Good morning. For some reason, I skipped over this section. So weird. Anyways, so today's section of linear algebra is eigenvectors and linear transformations. I'll just get out my notebook and okay. In this section, we'll look at eigenvalues and eigenvectors of linear transformations, where V is any vector space. In the case where V is a finite dimensional vector space, there is a basis for V consisting there's a basis for V consisting of eigenvectors of T. We will see how to represent the transformation T as left multiplication by a diagonal matrix. Okay. Eigenvectors of linear transformation. Previously, we looked at a variety of vector spaces, including the discrete times signal space S and the set of polynomials P. Eigenvalues and eigenvectors can be defined for linear transformations from any vector space to itself. Eigenvalues and eigenvectors can be defined for any linear transformation from it. Okay. Let V be a vector space. An eigenvector of a linear transformation is a non-zero vector in X such that T of X is equal to lambda X for some scalar lambda. A scalar lambda is called an eigenvalue of T if there's a non-trivial solution of X of T of X equal to lambda X. Such an X is called an eigenvector corresponding to lambda. So this is kind of like following the trend of this book is like it starts off with just matrices, and then it generalizes it to linear transformations. All right, example 1. The sinusoidal signals were studied in 4.7 and 4.8. Consider the signal defined by cos pi theta over 2. Cos k pi. Wait, hold on. What does this signal look like? Yeah, that's what I thought. It just alternates. Can I do list line plot? Oop. Wait, no, it's line plot, list line plot. That's what I thought. The left double shift linear transformation D is defined by D of x of k is equal to x of k plus 2. Show that sk Whoa, this is kind of crazy actually. Show that sk is an eigenvector of D and determine the associated eigenvalue. Okay, the trig formula cos theta plus pi equal to minus cos is useful here. So wait, what were the values? It went minus 1, 0, 1, 0. Okay. Oh, so the eigenvalue is going to be minus. Yeah, okay. So set yk equal to d sk and observe that yk is equal to s of k plus 2, which is equal to cos of k plus 2 pi, which is equal to, cos k pi over 2 plus pi, which is equal to minus cos k pi over 2. So this establishes that sk is an eigenvector Wow, this is a great example. Really stretches the imagination. That's great. That's super cool. So the vector itself is this infinitely infinite length list. In figure 1, different values for the frequency f are chosen to a graph section of the sinusoidal signals fk pi over 4 and fk pi and d. Okay. Setting f. So like this defines a vector in the vector space of signals S. Setting f equal to 2 illustrates the eigenvector for D as established in example 1. What is the relationship in the patterns of the dots that signifies an so wait, D is a linear transformation. I'm gonna write this down. This is actually really wild. Okay, so we have SK defined by the list cos of k pi over 2, which is a vector in S, vex space of signals. We define a linear transformation D by D of some signal xk is equal to the x of k plus 2, which is so shifting it to the left double shift. Oh yeah, right. It does shift it to the left. Left shift by 2. Okay. Show SK is an eigenvec of D. That's pretty crazy, man. So S of k, so D of SK is equal to S of k plus 2, which is equal to cos of k plus 2 pi over 2, which is equal to k pi plus 2 pi over 2 is equal to k pi plus pi. K pi over 2 plus pi all to cos. So then, but that's equal to minus cos k pi over 2. Okay, so that's what they get here, which is equal to minus sk. So since we found a vector that when transformed is just a scalar, then it's an eigenvector. So since d of sk is equal to minus sk, sk is an eigenvec and minus 1 is the associated eigenval. Okay, so then they plot different. Okay, what is the relationship in the pattern of dots that signifies an eigenvector relationship between the original signal and the transform signals? What other choices of the frequency f create a signal that is an eigenvector for D? I think if f was 4, because then it would just be the pi's, and so cos pi is -1, right? So then all of the terms would be -1 for all k. So that means that d of s or d of yk would equal yk. So okay, but then also 8, I think, if it was 2 pi. Figure 1, the graph on the left illustrates the sinusoidal signal with f equal to 1, and the graph on the right illustrates with f equal to 2. What are the green dots? Is that green or am I tripping? It looks green. All right. The matrix of a linear transformation. There are branches of linear algebra that use infinite dimensional matrices to transform infinite dimensional vector spaces. However, in the remainder of this chapter, we will restrict our study to linear transformation of matrices with finite dimensional vector spaces. Let V be an n-dimensional vector space and T be any linear transformation from V to V. To associate a matrix with T, choose any basis B for V. Given any x in V, the coordinate vector xb in Rn is the coordinate vector x corresponding to B. So that means the weights. I always get tripped up on this notation, but this means like the weights of the linear combination of the vectors of the basis B that equal x. So you would have B times x with respect to B is equal to x. As is in Rn, as is the coordinate vector of its image. Okay, so this would be B times T of x of B, T of x with respect to B is going to be equal to T of x, right? The connection between xb and this is easy to find. Yeah, let B1 to Bn be the basis. And if x is equal to this, then xb is this. That's what we said. It's the weights in the linear combination of the basis vectors that equals x. Okay, so then if we have this, we apply linearity to this expression because this is just substituting for x because t is linear. Now, since the coordinate mapping from V to Rn is linear, equation 1 leads to oh, okay. I think that makes sense. So, you take so T of x is going to be equal to this. That's fine. because we know that x is equal to xb. But now writing the transformed x in terms of this, okay, that kind of makes sense. Okay, so if we have t from v to v, and we have x, we have b is a basis for v, then we have b times x relative to b is equal to x. So that means that x is equal to the sum of if xb is equal to r1 dot 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 rn, then x is equal to the sum of r1b or ri bi. So that's the linear combination. Now if we want to find so also t of x is going to be equal to t of sum of ri bi, and this is going to be equal to ri or it's going to be the sum of ri t bi. That's what this is. This is by linearity. But so then t of bi is the vector of the basis elements. Okay. Okay, since b coordinate vectors are in Rn, the vector equation can be written as a matrix. Okay. I think the crows had like a baby, and they're like raising the baby. All right. So yeah, so then M is equal to this matrix of the basis elements T, or no, wait, T of B1 in B, dot, T of BI, or BN, I guess, in terms of B. Yeah, the matrix for the transformation T relative to the basis B. Okay. Notationally, uh, um, T with respect to B. Okay, cool. I'll draw that diagram. So we have X under T goes to T of X. Then here we get X relative to B. And then finally we get T of X relative to B. Okay. All right, now we get an example. Suppose B is a basis for V. Let TV to V, T from V to V be a linear transformation with a property that B1, B2, basis of V. And T from V to V, linear map. Okay. Such that T of B1 is equal to 3B minus 1 minus 2B2. And T of B2 is equal to 4B1 plus 7B2. I'll be back. All right, I need to think about what this means. So this means that t of b1 relative to b is just going to be the vector 3 minus 2. And similarly for t of b2 relative to b is going to be equal to 4, 7. So then our matrix M equal to t relative to b is equal to 3, 4, minus 2, 7. And so what t of what so what t uh, of b takes a vector in the basis b and returns yeah wait, because if we have b times x b, we get x. So in this case we have, but in this case you get t of x relative to b. So if we did an example, like let's take x equal to, all right, so we can just write out this example for real. So let's just start up our uh, okay, but the point is, okay, TB2, so this is um what this really is this is T B1 relative to B. Okay, so then we get, TB is equal to this, and this just needs to be 4, 7. The part that's missing for me is finding M was easy, but the point that this mapping M, that M is the thing that takes a vector relative to the basis B and returns a vector relative to the basis B. I feel like I want to work an example out just like directly on that. Okay, The mapping from T to P, from P2 to P2 defined by so we have T from P2 to P2 defined by T of A0 plus A1T plus A2T squared is equal to A1 plus 2A2T. Oh yeah, this is the derivative. Find a basis matrix for T. Find the B matrix for T. So that means find, so if B is the basis 1T T squared, find T relative to B. And what does that mean? That means that so we want to find, so T of B is the matrix, of T of BI relative to B. So so we need to write, so first off, we're going to take our first base element, which is just 1, and we're going to apply T to it. So we're going to get equal to 0. It's nothing, right? So then so now we need to write 0 relative to B. So then this is going to be 0, 0, 0. Well, but hold on. That's crazy. Someone tell me if I'm alive. Am I alive? I think I am. We've been having internet problems the past couple of days. Okay. So and then finally T of T squared. So wait, we need to write 1 relative to B, which is just going to be 1, 0, 0 is equal to 1 to B. And then T squared is equal to 2T. And 2T is 0, 2, 0. So I think that our columns are 0, 0, 0, 1, 0, 0, and then 0, 2, 0. Okay, cool. That's what I got. And then B is, so this is T relative to B. So what does that mean? That means that we can write a vector in the basis B, and multiply it by this, and we get t of x relative to b. Okay, that sort of makes sense. So now verify that verify t of p relative to b is equal to t relative to b times p relative to b for all p in P2. Okay, so if we let p equal just A0, A1, A2, like in the definition of the transformation, then t of p just generally is going to be a1 plus 2a2t by the definition of it, but then that relative to b, so then tp or tp relative to b would be right, that is going to be like a column vector, and it's going to be a1 2a2 0. Now what we want to do is we want to take our matrix. Yeah, so that was the left hand side. Now the right hand side is going to be. Wait, why don't I just set this up? I don't know why. I should be setting this up more often. Give me a second. I'm gonna get my paper. Okay, so let's do this. Unlock this. We'll get it like 70. Okay, that looks pretty good. All right. So what we have here is t of p relative to b. Now we want to do, so this is, now we want to do t of b times p of b. So this is just going to be the matrix vector multiplication 0, 1, 0, 0, 0, 2, 0, 0, 0 times, and now p relative to b P is an arbitrary A0 plus A1t plus A2t squared. So this is equal to P. So now P relative to B, so PB is just going to be A0, A1, A2, 2. Just the coefficients. So this is going to be A0, A1, A2. And so we'll see here that we're going to get A1 plus 2, A2. And here we got the same thing. So this really, I guess, would be, this isn't like this. It would be, it would be A1, 2A2, 0, which is what these things are equal. So therefore, we did it. All right, so we can switch back over to this and see if they did it the same way. So they take a general P. Cool. This is a good picture. I actually really like this picture. All right, linear transformations on Rn. In an applied problem involving Rn, a linear transformation T usually appears first as a matrix transformation. If A is diagonalizable, then there is a basis B for Rn consisting of eigenvectors of A. Theorem 8 below shows that in this case the B matrix for T is diagonal. Diagonalizing A amounts to finding a diagonal matrix representation Okay, so suppose A is diagonalizable, and this is the definition of diagonalizable, i.e. it's similar to a diagonal matrix. This is, where P, the definition of, because we just went over this, so we should probably reinforce it, is that the definition of similarity is that there exists some invertible P such that P, D, P inverse is equal to A, then A is similar to D. Now, if D happens to be diagonal, then A is diagonalizable. Okay. Where D is the diagonal n by n. If B is the basis for Rn formed by the columns of P, then D is the B matrix for the transformation A to AX. Denote the columns of P by B1 to Bn so that B is equal to, okay. AB1 relative, that's the part that AB1 relative to B is equal to, oh yeah, right, because this is going to be a vector relative to B. So then we can say P inverse A B1. So what was the theorem? The theorem is that then D is the and so we need to remember that if this is the case and D is diagonal, then the elements on the diagonal are the eigenvalues, and then the columns of P are the eigenvectors. So if B is the eigenbasis of A, then D is the B matrix transformation. Right. So D is the eigenbasis is the eigenbasis transformation, basically. Okay, so I'm gonna this seems like pretty cool actually, so I'm gonna write this down. Theorem 8. So A diagonal, i.e. A is equal to P D P inverse, where D diagonal. Then cols of P is eigenbasis. Okay, now it turns out that for T equal to T of X equal to A of X, the T of B, meaning the matrix that sent the matrix or whatever that sends a vector relative to the basis B to the vector T of X relative to B, i.e. T of X relative to B. And what that means is this is actually a really cool theorem. This is called the diagonal representation. Diagonal matrix representation theorem. Okay, so let's understand this proof a little bit more deeply. Denote the columns of P by B1 to Bn, so the basis is B1 to Bn, the set. Then we have this as the columns, or the matrix really. In this case, P is the change of coordinates matrix PB discussed in section 4.4. Okay, so we're going to get, so the proof, we have P is equal to B1, Bn, where B is equal to the set Bi. Okay? P of X relative to B is going to be equal to X. And X relative to B is equal to P inverse X. So if T of X is equal to AX for X in Rn, then we want to show what? What is this theorem actually stating? We want to show that D is equal to T of T relative to B. So that's what this means. D is the B matrix of the transformation is this thing. Whoa, how did I get so many views already? What the hell? What's going on? Okay, so the next step, so let's walk through the proof now. So now that we know what everything means, so t of x equals a of x, and we're trying to show that the transformation t relative to b is equal to d. So we have t relative to b. And the definition of t relative to b is just going to be you take the transformed basis, so tbi, and then you write those transformed basis vectors in terms of the basis b. Okay, so this is by the definition of t of b. So what? Just to be super clear, so we can do just to reinforce this, we get t of b times x of b is going to be equal to t of x relative to b. Okay, so we can rewrite this so this is going to be equal to the matrix A times bi relative to b. But since we have, if you let this be like, I don't know, yi or something, relative to b, then we know that by this, can you see that? Then this is going to be equal to p inverse yi. So then we're going to get we should get p inverse times a bi. Okay, and remember that this I here means that we have a list of column vectors. Okay. And then almost okay, so we have okay, but what this is equal to, just to really rewrite it, we get p inverse a b1 and these are all like columns, p inverse a bn. But we can actually factor this out into p inverse a times b1 to bn, which is equal to p, and this is p. So we have p inverse a p is equal to t of b, but this is also equal to d because by A equal to P dP inverse. Oops, my bad there. That proof's a little technical, honestly. Proof's a little. To understand what that means seems tricky. Actually, okay, it's actually not that complicated. I feel like they didn't say it as well as they could have. Imagine that you have some vector relative to the eigenbasis. Okay? What does that mean? That means that if you have some transformation A, that acts on whatever Rn, or I don't know if it even matters, then the action relative to the eigenbasis is just going to be scaling it by the eigenvalues for each, element of the for each weight of the linear combination of the eigenvectors. So that's actually like not that complicated. But I am glad that we went through it because I feel like that is a pretty cool theorem. All right, example 4. T from R2 to R2. Find a basis B for R2 with the property that the B matrix for T is a diagonal matrix. Okay, I'll be back in a second. Diagonalization is actually a very powerful tool. No, what are the conditions on something being diagonalized? Well, I know that it has to be similar to a diagonal matrix, but can you have multiplicities and still have it be diagonalizable? I know it has to be diagonalizable, but that just sort of uses a circular definition. Right. Oh, okay, yeah. So, right, the eigenvectors need to be linearly independent. Wait, the kernel? Yeah, the dimension of the kernel. Okay, so I like this one. The eigenvectors need to be independent. All right, so let's figure out this example. So they give us P and D. What are we trying to find? We're trying to find a basis B. I feel like only under the motivation of eigenbases does it even really make sense to do change of basis. So this whole book is actually starting to make sense because it's like, it's really like, why would you use any other basis? But then you see eigenbases and you're like, okay, that actually makes sense. That's chill. That's cool. Oh, wait, did I switch it back over? Yeah, I did. Okay. The proof of theorem 8 did not use the information that D was diagonal. Hence, if A is similar to C, then C is the B matrix. So we got to get used to that terminology. The B matrix means some transformation, some map, some linear map relative to a basis. All right, this section is going to take a while because it's a pretty dense section and it's definitely important. Okay, conversely, if T from Rn to Rn is defined by T of x equal to A of x, and if B is any basis for Rn, then the B matrix for T is similar to A. Yeah, that makes sense. In fact, the calculations in the proof of theorem 8 show that if P is the matrix whose columns come from the vectors in B, then the B matrix of T is equal to well, wait, the set of all matrices similar to A coincides with the set of all matrix representations of the transformation A to AX. Representations of the transformation A to AX. I wonder how crows feed their young. Do they do the thing where they throw up the food? Do they do that? I don't want to look that up on screen, but I am curious. Okay. The character, but the eigenspace for the eigenvalue -2 is only one dimensional, so A is not diagonalizable. However, the basis B has the property that the B matrix for the transformation is a triangular matrix called the Jordan form of A. Hmm. Okay, this is like thrown in there, but this seems just kind of thrown in there. I don't really get that at all. An efficient way to compute the B matrix P inverse AP is to compute AP, then row reduce the augmented matrix. Oh, interesting. I'll write that down. Wait, I think I actually misunderstood something because TB is called the B matrix, right? So the B matrix So C is the B matrix of the transformation x to ax. Okay, yeah. All right, let's look at the practice problems. Ooh, I just used the last page. I'm gonna go get my. Well, actually, no. Hold on. I still have more in this notebook, but I bought a new notebook for like freaking like $8. What a ripoff! Am I right? I think I got 10 of these for $8. However, I'm so sick of. I don't know if you can see this, but it bunches up. It bunches up right here because the spiral is so bad. So anyway, so I got like a fancy Japanese stationary that, anyways, I'm excited to try out a new notebook. I do think that I'm not happy about having to spend $8 on a notebook. I feel like that's kind of insane. It's just paper, but maybe I think I might be able to find it cheaper on Amazon. At least one with a spiral that doesn't suck. Because I don't know if I would be willing to spend like 10 times as much, but maybe like 4 or 5 times as much. All right, problem 1. Let me just write it down and then we'll switch over to the cam. So t of a0 plus a1t plus a2t squared. Wait, find this. Find t of if t from P2 to P2, where TB is equal to the matrix 3, 4, 0, 0, 5, minus 1, 1, minus 2, 7. All right, switch over to the camera. Okay, so I kind of wrote this wrong terribly, but that's T. T of find this if we have this. So what this equals is this is going to be T of B1 relative to B, T of Bn relative to B. Okay, so that okay. So since I forgot to mention B is equal to our standard polynomial basis. So then this means that that the vector 3, 0, 1 is equal to 3 plus t squared. Because this is a B vector of t b1. So then for 4, 5 minus 2, we're going to get 4 plus 5t minus 2t squared. And then finally, 0 minus 1, 7 is equal to minus t plus 7t squared. So if this is P, if we let this be P, then P relative to B is going to be the vector, the column vector, A0, A1, A2. So if we're trying to find T of P, right? But we're given, so find T of P given T of B. So then we want to find, so then P relative to B is this. So then all we have to do is, so this is A0, A1, A2. Then we have to just find T of B times P of B is equal to, this is going to be T of P relative to B. But so then I think we then need to apply P inverse. So I'm pretty sure then we have to go P inverse. Or wait, hold on. I'm trying to think about that commuting diagram. If we have like X, then we have like T of X, or let's do P. If we have then T of P, then we have P B, and we have this is going to be T of P B. Now, how do we go this way? So this is but I think since B is the standard basis, so I'm sort of using B kind of as a in a incorrect way, because I'm referring to B as a basis as in that it's a set and as a matrix, but I think it's just going to be equal to 1, 1, 1, 0, 0, 0, 0, 0, 0, equal to the identity matrix. And the inverse of the identity matrix is the identity matrix. So I'm pretty sure that T of P is equal to T B times. This is a good example because it didn't actually require a lot of like random stuff, but it was like insightful. So let's just look at the answer. Cool. Okay, I'll write down this next one. A by C, B n by n. The text has shown that if A is similar to B, then B is similar to A. This property, together with the statements below, shows that similar to is an equivalence relation. That's cool. So we already showed symmetric. We just need to show transitive and reflexive. So so A is similar to A. Take P to be the identity matrix. The identity matrix is obviously invertible, so we're good there. So now B, if A is similar to B and B is similar to C, then A is similar to C. So in that case, we have A equals P1 B P inverse, right? And then we also have that that B is equal to P2, or this is P1, P2 C P2 inverse. So then if we substitute Here, I'll switch over now. Okay, so this is problem 2. Okay, so we can substitute in. We could say A is equal to P1, P2, C, P2 inverse, P1 inverse. Now, if we have just a generic, let's say X, Y inverse, I think how do we prove that this is the case? Because I'm pretty sure we went through this proof earlier in the book, but I just don't remember. How do you prove that? Anyways, I'm pretty sure that this is true, so then we just take P3 equal to P1, P2, thus it's invertible because is it actually always true that composition of invariable square is invariable? So yeah, we need to do this proof, but it all relies on this proof, because then A is equal to P3 C P inverse of. So that is. Wait, did I get a chat? For some reason, my chat's not showing up. Let me get on my phone. If you said something, give me a second. I need to turn on my phone. Okay. So yeah, for some reason it's not showing up on my computer. Give me a second. I will read it. All right, so let's see how they do it. But we definitely need to. Okay, A, yeah, I just take it as the identity. That one's obvious. Oh wait, it's P inverse. Wait, does it matter? I don't think it matters whether or not you do P inverse AP or whatever. Oh wait, what was the problem? A is similar to B. B is similar to C. Oh, okay. Right. So they an inverse about a fact about the inverse of a product. Okay, my phone's on. Give me a second here. Did I actually get any chat? It says 0. Oh, whoa, there's a ton of chats. Damn, there's a ton of chats. What the hell? Yo, I didn't see any of these chats, guys. What is up, man? We're studying linear algebra. I don't know if you guys are still here, but yeah, for some reason my stream setup did not give me any of those, so I'm watching them now. All right, so wait, but we want to go through the proof for square invariable matrices A and B that AB that inv of AB is equal to inv B inv A. Because I forget about that proof, but that's the proof that we need to go into. By hypothesis, there exists A inverse and B inverse, such that A inverse equals I, and it's commutative. We claim that. Oh, okay. We claim that. Okay, so the proof is assume A inverse equals I, and B inverse equals I. Suppose that P is equal to B inverse A inverse. Then we can, to prove this, we can check A, B, P is equal to I. Oh, yeah. So then you get A, B, B inverse, A inverse, and then you can cancel the middle, and then you cancel the outside. Okay, right. So there we go. So that one was, yeah, associativity is crucial. But if you're dealing with non-associative algebras, why don't you just go somewhere else? Okay. Wait, what? Oh no, yeah. I was like, wait, are there no exercises? It's just being dumb. All right, so now we do our classic read through all of the exercises and decide which ones to do. All right, so let's just go through the exercise. B is a basis. Let V be a linear map with the property that they give you. They give you basically the B matrix of T. So this is just going to be writing down these vectors as columns. So what we can do that one. That one's fine. It's actually getting a little warm. I'm going to take my sweater off. Okay, so that one's not so bad. Okay. This is like the best section I think I think this might be the most cool section that I've had in this book. I mean, eigenbases are just so dope. And you kind of need to know change of basis to understand eigenbases. Or at least diagonalization. All right, problem 2, you go to basis, find the B matrix. Okay, so we can skip 2, but we'll do 1. Assume the mapping T from P2 to P2 is defined by that as linear. You assume it's linear. Okay. Find the matrix representation T relative to the standard polynomial basis. All right, I'll do 3. I haven't done like a ton of problems and gone really hard in a while. So I do kind of want to just like go hard. All right, problem 4. Oh, that's interesting. Oh no. Am I back? My internet keeps cutting out. I think I'm back. Okay. So this one, so find T of P when P of T equals this. Is P an eigenvector? All right, so yeah. 4 is a good problem. Let B be a basis for V. Find T of 2B minus 5, B1 minus 5, B3. When T is a linear transformation whose matrix relative to B. Okay, so what does that amount to? That amounts to because we have T of X, but this vector is like relative to B. So XB we know is equal to 2, 0, minus 5. Sorry, I shouldn't be doing these because we're going to do them later, but I just want to go through it. So in this case, so we have the B matrix. So this is just going to be a matrix. I mean, you gotta be fast at recognizing when it's just a matrix vector multiplication. And this one is, you just take this as XB, the B, whatever. You guys know what I'm talking about. Okay, so we'll go through that though. This is the same one. They like the repetition. Find the B matrix of the transformation. So, okay, so what does this amount to? We're definitely doing 7 because I need to practice on that. or we'll do 5. We'll do 5 just so we can check our work. But what does this amount to? So we need to, in this case, we need a we just need to find. So basically, we just need to find the matrix that A is similar to under the change of basis that's given by the matrix B. So so what you do is you form. So what you're gonna do is you're gonna multiply. So for 7, you're gonna have B. I'm gonna call B the like horizontal concatenation of these two vectors, and you're gonna have B inverse AB, and that's gonna be equal to C, which is the B so and C is the B matrix of X to AX. Okay, so that amounts to just a couple of. You can do the row reduction thing. They said that in that tip that where did they say that instead of. Where did they say that? Oh yeah, it was the numerical notes. But we're probably going to use a computer to do the matrix multiplications. But so we'll just compute the inverse. 8 is the same thing. Maybe we'll do 8. I feel like practice on that would be pretty good. Okay. So we want to find the. Okay, so 9 and 11 for sure we're going to do. Basically, it's find the eigenbasis and then find. Or what it's saying is find the B matrix of A, but the B matrix of A needs to be or I guess you could call it T. Yeah, find the B matrix of T, require that it's diagonal. So you need to find the eigenvalues and the eigenvectors, and then you just form the A equals PDP inverse. And we'll check our answers on all of this stuff. I always check my answers at the end because how else do I know if I got them right? Okay, 13. Let A be as a basis. Verify that B1 is an eigenvector of A, but A is not diagonalizable. Find the B matrix for T. Okay, we can do 13. So what does this actually amount to in solving this? So first off, you need to just multiply A times B1, and then you see if the result is a scalar multiple of B1. Then if it is, then it's an eigenvector. If not, then it's not an eigenvector. Now to show that A is not diagonalizable, to show that if someone handed me a matrix and said, show that this thing isn't diagonalizable, I would find all of the eigenvectors and then determine the dimension or the rank. I would determine the rank of the set of eigenvectors. And if it was less than the dimension of A, then I would say it's not diagonalizable, because for something to be diagonalizable means that it has a spanning eigenbasis. That's an if and only if. We just went over that, right? A square matrix has a basis of eigenvectors, i.e. a spanning eigenbasis, if and only if it's diagonalizable. Okay. Okay, problem 14. Define T from R3 to R3 by T of X equals A times X, where A is a 3x3 matrix with eigenvalues 5 and minus 2. Does there exist a basis B? $14 is good. 14 is like one of those theoretical ones. When you start to get to the like past the, because like the first 15 of these in this book is always just like computational, but then it starts to get pretty good. Like then these problems can actually get pretty puzzling. All right. 15, define T from P2 to P2. Find T of P when P of T equals. Whoa. I like these polynomial ones. These polynomial ones are fun for me. So, okay, so you take. So this is just apply it, right? So you just take P of 1. So this is going to be 1 plus 1 plus 1. So this is going to be 3. And then P of 1 times T is going to be 3T. And this is going to be 3T squared. I think it is an eigenvector because the action is a scalar multiple of P of T. So then T of P is equal to lambda P of T. Therefore, so we already did part A. And then we'll do part B. So I'll do 15. 15 seems actually pretty fun. Honestly, even the act of just reading all the problems. Okay, so 16 we can skip because it's kind of the same thing. It looks a little bit like a harder version of it, but it is the same thing. True falses, we always do true falses. So 17 through 20. Let's just read through them. Similar matrices have the same eigenvalues. Similar matrices have the same eigenvalues. I don't know. I think so. But why? We'll definitely need to go through that. And then similar matrices are the same eigenvectors. I think that's actually not true. I think they're like inverses in a way. Okay, 19. Only linear transformations on finite vector spaces have eigenvectors. That's false. We showed that at the beginning of the section with the vector space of signals, discrete signals. Okay. If there's a non-zero vector in the kernel of a linear map, then 0 is an eigenvalue of T. Hold on. If there's a non-trivial null space of some linear map, then then it's not invertible. I think that's false. I don't think you're guaranteed that 0 is an eigenvalue, but I think if T was invertible, then you know that 0 isn't an eigenvalue. So I think that one's also false. But we're gonna check all of those. Providing justification for each case matrices are square. If A is invertible and similar to B, then B is invertible. Oh, these ones are fun, man. Ooh, similarity, things like this is fun. Explain. So hint, P inverse AP is equal to B for some invertible P. explain why B is invertible. Then find an invertible Q. Okay, 21 is cool. We're going to definitely do 21. 22, if A is similar to B, then A squared is similar to B squared. A equals P, B, P inverse. Then we multiply both sides by, okay, then we right multiply both sides by P. So we get AP is equal to PB. Then we left multiply by A. So then we get A squared P equals APB. And then we right multiply by P inverse. We get A squared is equal to APB P inverse. No, that doesn't do what I want. All right, 22 seems pretty good too. If B is similar to A and C is similar to A and B is similar to C, we can skip that one. Once you have transitivity like that, you can just like since we already proved this equivalence relationship, that one becomes trivial. So since we already did the equivalence relationship thing, B is similar to A, C is similar to A, and B is similar to C. So that's more like a V. So you have B to A and C to A. Now you're trying to find this thing. If I have an equiv relationship tilde and B tilde A and C tilde A, how do we prove B tilde C? Since it's symmetric, okay, yeah. So it's just a direct application of the fact that it's equivalence relationship. Man, I remember when I first learned equivalence relations. I was like, I just like did not get it. Like, I was trying to watch these videos. I was in the library and I was just like, what the hell are these guys talking about? Like, there was just no, like, all of the videos that I tried to watch, there was just like no motivation or anything. It's like they didn't say, okay, look, we want this generalized notion of equality, and they didn't say any of that. They're just like, okay, this is reflexive, symmetric, and transitive, and it's like, what does that even mean? And to make matters even worse, I mean, I was really in a course that was like aimed at people that already knew math, but like the professor was so bad, and he was like, let's call this symbol box, and then he's like, oh, let's make it like a box with a dot in it, and he like just like complete nonsense, just total nonsense. Anyways, that's the power of having a terrible teacher. It's just like completely confuse you as to why we're learning it at all. If A is diagonalizable, and B is similar to A, then B is also diagonalizable. So 24 is a good one. 25, if P equals P inverse AP, and X is an eigenvector of A corresponding to lambda, then P inverse X is an eigenvector of B corresponding to lambda. So if we did like, so if we have like P or BP inverse is equal to P inverse A, and then we multiply both sides on the left by x. Then we get p, or b p inverse equal x is equal to p inverse ax. But since x is, we assume the eigenvector, then we can just write this as p inverse lambda x, which is equal to lambda p inverse x is equal to b p inverse x. So yes, that's true. Okay, that one was easy. 25 is easy. I just did that one, but I'll show you it on paper in a second. But this one's easy because when you have you end up with b p inverse x is equal to lambda p inverse x. So then p inverse x must be an eigenvector. So that one's easy. Oh, my trackpad's not working anymore. All right, if A and B are similar, they have the same rank. That one's pretty good. I don't know how to prove that. Man, this is one of these sections where like you really should do every exercise because you got to understand this stuff. The trace of a square matrix is the sum of the diagonal entries in A, and denoted by trace A. It can be verified that the trace of f times g is equal to the trace times g times f for any two square matrices f and g. Should if A and B are similar, that their traces are the same. Oh, wow. 27, I would have never really guessed that. That's pretty cool. 28, it can be shown that the trace of a matrix A equals the sum of the eigenvalues. That's always true? Oh, okay, you verify for when it's diagonalizable. Wait, that's actually crazy. The trace of A is equal to the trace of its or the sum of its eigenvalues? Wait, that's crazy. What? The trace of A is equal to the sum of eigenvalues? That's true for any square. It can be shown that the trace of a matrix A equals the sum of the eigenvalues of A. Verify when it's diagonalizable. So you say A is equal to PDP inverse. Um, 28's crazy. We got to do 28. I don't know how to do it. Ooh, okay. All right, so we're actually getting to the end of it. I usually don't do these calculator problems because they're kind of boring. Okay. Refer to the space. Ooh, show that moving average is okay. Exercises 29 through 32 refer to the vector space of signals S from section 4.7. The shift transformation S shifts each entry one position to the right. The moving average transformation M2 takes the sum of yk and yk minus 1 divides by 2, creates a new signal by averaging two consecutive terms in the given signal. The constant signal of all ones is given by chi. Okay, this is kind of strange notation, but I'm chill. And the alternating signal is minus 1 to the k. Okay. Show that chi is an eigenvector of the shift transformation. Okay, yeah, because if you shift it, you get the exact same sequence. So the eigenvalue is 1. So 29 is obvious. The shift transformation, the eigenvalue is minus 1. We already kind of did that one. Okay, show that alpha is an eigenvector of the moving average transformation. First off, it's not even clear to me that this is a linear map. So for me, I need so we're gonna do 31 and 32, and that'll be it. That'll be the last problems we do. But I would like to prove that this is a linear transform. This is a linear map for any two signals, or for any signal yk in S. We just need to show that if we have like M2 of let's say lambda 1 y1, where y1 is a signal, plus lambda 2 y2 is equal to lambda 1 m2 of y1 plus lambda 2 m2 of y2. So we just need to unwrap the definition of what it means to be a linear map, and then we show that they're equal, and then we're good. Then we know it's a linear map. But I it's not obvious to me that this is a linear map, so I feel like it's worth going through that. Okay, so those are all the problems. I'll be back in a second to hammer out some of these problems. I might also get my computer mouse because sometimes my trackpad just completely fails. All right, I'll be back. Hola. 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 Okay. All right, so let me just write them down in here, which problems we're actually doing. So we're doing 1, 3, 4, 5, 7, 8, 9, 11, 8, 9, 11, 13, 14, 15, 17 through 20, 21, 22, 24, 25, 26, 27, 28. Those proof ones are always really good. And then 31, 32. All right, those are the problems for section 5.4. All right, we got a lot of problems, but that's chill. Okay. I gotta get amped up. Let's see, how long did it take just to get through that? It took 2 hours just to get through the section. But that's what it takes, bro. That's what it takes. You know what? Should we use the cool paper? I'm gonna use the cool paper. Should I use the cool paper? Let's see. I only have like 20 sheets left of this. I just want to see what it's like. I just want to try something new. I'll be right back. Okay, all right. So, check this out. Oh yeah, unruled paper. It's clean. Okay. Linear algebra 5.4. Okay, we're going to do problem 1. B is equal to B1, B2, B3. Basis of V. T from V to V. And we have T of B1 is equal to 3B1 plus 5 minus, and T of B2 is equal to minus B1 plus 6B2, and T of B3 is equal to 4B2. Okay, so the problem is find T relative to B. Okay, so we know that this, if we write T B1 is equal to 3 minus 5, then T of B2 relative to B is equal to, wait, actually, this is a weird, okay, yeah, so it's kind of a, this is going to be minus 1, 6. Oh, this needs to have a 0 here. That's why I was tripping out. This needs to have a 0. And this is going to be 0, 4, 0. So our matrix, T of B, is equal to, these as column vectors. 3, minus 5, 0, minus 1, 6, 0, 0, 4, 0. Easy peasy, bro. Okay. So what did we do? We crossed off problem 1. So now we're doing problem 3. I will show the problem 3 in here while I write it down. So we say T is a map from polynomials of degree 2 to polynomials of degree 2, such that T of A0 plus A1T plus A2T squared is equal to 2A0 plus 3A1 plus 4A2T plus 5A0 minus 6A2T squared. Okay. And we assume it's linear. Okay. The problem is find T be relative to the standard basis on the polynomials, B equal to the set 1 T squared. Okay, we can switch over to this. Okay, so remember, T of B It's always is defined as, t of b1 relative to b, dot, 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 t bn b. So that's just the definition. Now, what we can do is we can write so let's say let p equal a0 plus a1t plus a2t squared. Then p relative to the basis b is a column vector a0, a1, a2, okay? Okay, so now what we need to do is we need to find t of b1, which is equal to t of 1. So t of 1 means replacing t with 1. So this is going to be equal to, this is going to go to, so this is, so wait, let's just write, so let's just write 1, the polynomial 1 in the basis b is just going to be vector 1, 0, 0, right? Okay, so it's not replacing it with t. Yeah, no, that's dumb. It's not replacing it with t. That's not right. So, so we're gonna say a0. So our polynomial. So this is equal to. So I think it's just gonna be 2 because we're basically, if we were to write this as a set of rules that we're replacing, one a0 goes to 1, a1 goes to 0, and a2 goes to 0. So in that replacement, then we're going to get 2, and then this is 0 and this is 0. So then that's 0. But then finally we're going to get plus 5t squared. Okay, so that's important. Okay, then t is the second basis element relative to b is going to be the column vector 0, 1, 0, right? So now this is going to be equal, so then t of the polynomial t is equal to, and so this is the rule where a1 goes to 1 and everything else goes to 0. And that means that this becomes 0, so we're going to get 3, so we're going to get 3t plus, and that's it, 3t. And then finally, t squared relative to b is equal to 0, 0, 1, t squared is equal to. So this is going to be the rule. This is going to be the rule where we're going to get 4t minus 6t squared. Okay, so what these all are, so this thing, and this thing, is it's going to be, each of these, this is like T of B1. Yeah, this is T of B2. This is equal to T of B3. So now all we need to do is write these in their non-polynomial but vector forms and then form this. So this is going to be the answer, and it's going to be, so we take our coefficients, right? So we're going to get 2, 0, 5. So the first one is 2, 0, 5. And the second one is going to be 0, 3, 0. And the third one is going to be 0, 4, minus 6. Okay, let's just double check our answer. Two plus 5t squared. All right. Heck yeah, we did it right. All right. So we did. I like delete it. Well, let's not delete them, but let's whatever. That's fine. So we're going to do problem 4 now. And problem 4 is let t from P2 to P2. Guys, drop in the chat. What's your favorite vector space? What's your favorite vector space? All right. Where T of P is equal to P of 0 minus P1 T plus P2 T squared. Part A, show T linear map. Transformation's too long of a word to write, guys. Drop in the mud and jab. What's your favorite freaking vector space? Okay. Show that T is a linear transformation. So what does this mean? So what we're going to do is we're going to take an arbitrary element of P2, and then we're going to show that the action of this, or here's what we're going to do. Okay, I know what to do. So let's move this all down. So problem 4, show that T is a linear map. So we're going to basically take, let P equal A0 plus A1T plus B, or A2T squared. Then let Q equal B0 plus B1T plus B2T squared. Okay, now what we're going to show is, and then let C1 and C2 in R, random constants. So we're going to have random constants. Now what we're going to do is we're going to figure out what happens if we do T of C1P plus C2Q. And if this is equal, put a question mark there, to, excuse me, to C1 of T of P is plus C2 T of Q, then it is a linear map. So, so let's first do this. So, C1 times So let's say this is equal to x. I'm going to call this x. So x is equal to this plus c2 b0 plus b1t plus b2t squared. Okay. And T of P is P0 minus P1T plus P2T. So so P of 0, so if this is x, then x of 0 is equal to, basically all the t's are going to go to 0, right? So then we're just going to get C1 A0 plus C2 B0. Now x of 1 is equal to, isn't it going to be, oh, this is going to be a mess. So this is going to be like, C1A0 plus C1A1 plus C1A2. So this is going to be just CA0 plus A1 plus A2 plus, this is C1, C2, B0 plus B1 plus B2. Okay, so that's x1. Now we need to compute x2. x2 is going to be equal to, this is going to get real messy, because this is going to be, so this is going to be, I think it's just going to be C1 times A0 plus 2A1 plus 4A2 plus C2 times B0 plus 2B1 plus 4B2. Okay, so this is, so now we need to construct T of P. So T of X is going to be equal to C1A0 plus C2B0 minus C1A0 plus A1 plus A2. Okay, and then finally plus this guy, which is C1A0 plus 2A1 plus 4A2 plus C2 B0 plus 2B1 plus 4B2. And then, all right, so now that we've done all this algebra, I'm tired of writing. Let's just go in and do it with some computer program. So, Sorry. Okay, so wait, are we back on my screen? Okay, so let's just figure this out. So we're going to get T of P is going to be defined as P of 0. So wait, so let's see, how do I do this? So if I have P of X is equal to P slash dot does that work? So if I have P is equal to A0 wait, do I need this? There we go. So if I call P of 0, does this work? So that doesn't work because this because we can just do this, right? This is going to work. Okay, so then we can just do wait, actually, if I do P slash dot T goes to list 0, 1, 2, does this work? This gives me a list, right? Hell yeah. So then we can just do dot 1 minus 1, 1. So this is for an arbitrary. Oh, wait, but you know what we have to do? We have to do minus T squared. That's what we have to do. There we go. Okay, so this gives us. So let's just say. So this is going to be T of P. So we need to do this is equal to this. So now if I have P, I can call T of P, and it will give me the transformation. So now what we need to do, oh my gosh, it's so dusty right now. I'm probably ending the stream early today. Hey Google, set an alarm for 1 hour. Okay, so we have 1 more hour of this stream. All right. So this is sick, dude. I'm getting so good. Okay, so now what we want is Q is equal to B0 now we want T of C1 P plus C2 Q. And we simplify. And what we want to do is we're trying to show, okay, so wait, let's just do this. So this equal to C1 T P plus C2 TQ. True. All right. So we just showed the linearity of this whole thing. Man, that took a while. Find T of P when P of... Okay, so now we can just do this. This is easy. So minus 2 plus T. Let's call it let's just call it P, or P2 is equal to, this is gonna be minus 2 plus T, right? Is it an eigenvector? Is it an eigenvector? No, it's not an eigenvector. Okay, so yes, so for A, yes, it's linear. For B, no, P of T equal to minus 2 plus T, not eigenvec. Because this is not a scalar multiple of okay, find the matrix for T relative to the, okay, so now what we want to do is we want to factor this. So wait, if I take this again, or wait, not that, hold on. No, we can just take T of P, and we get this. But what we want to do is I have this in Wolfram. How do I make it so that it collects the coefs based on powers of T, i.e. like because how is it collecting now? It's collecting collect, expand, T. Collect, expand, hash, T, and. Wait, there's powers of. Wait, what? That doesn't seem right. Wait, this. Wait. This isn't right, is it? The 0, 1. Oh, that's right. And then this gets dotted. I think that's right. Wait, what is T of P? Or wait, we have P, and then we have T of P. Oh, there we go. Okay, so there was actually a bug. So we need to actually check this again. Okay, cool. So it's still a linear map, but now we need to check this because this probably is wrong. And it is. Yes, it is. It is an eigenval. Okay. Um, um, so what are we doing here? We're doing this now. Okay, cool. So that was kind of a fun bug, actually. I like that. Operator precedence issue. That's the problem with having such a flexible parser, is that there's always a question of what the operator precedence is, and you kind of just have to be wary. So, um, what are we doing here is we're trying to figure out okay, so now we're trying to find what the the B the B matrix relative to this is. So that means like find the So what does that mean? That means that we get like some so for C, we have like T relative to B times some vector X, which is a polynomial relative to B, is going to be equal to T of X as a relative to B. So what am I trying to do? Because this is, what is this? This is T of an arbitrary element of P. So if we write this in terms of the basis, I think I did this wrong. What we need to do actually instead is we need to write, so if we wrote B is equal to 1t t squared, then we did T of B. Is this gonna work? How do we do this? Isn't there this thing called thread or something? Oh, because you know why? Yeah, because we should have just done this as like oh, but you know what we can do? So we could write it also as B1 is equal to, this would be like, no, because it expects it in polynomial form. All right, so let me just do it. So what we're trying to do is we're trying to take this polynomial 1 and turn it into 1 of 0 minus 1 of 1 t plus 1 of 2. And when I say this, it means the replacement of t with and then t squared. So this is just going to be 1 minus 1t plus 2t squared. So this is the first basis element. Then the second basis element is going to be t goes to, that's going to be t of 0, which is going to be 0, minus t, this is going to be 1t, so this is going to be minus t, plus, and then this is going to be t of 2, which is going to be 2t squared. And then t squared goes to, so this is going to be t squared replaced with 2, right? So this is going to be 4 minus, this is going to be, again, 4t plus 4t squared. Is that right? So maybe I should figure out what the code needs to be so that we can like do this properly. So why didn't t of 1, because what does t of 1 do? Wait, that's weird. So if it doesn't find the replacement, it doesn't, all right, if p equals 1, and we're trying to do the replacement, p goes to, or t goes to 0, 0, 1, 2. Yeah, then we just get the expression 1. Actually, that's not ideal, because you do want it to be 1, 1, 1. Anyway, so I think that the basis b is going to be, or TB is going to be 1, these are, we'll transpose it, I guess. Yeah, we'll just transpose it. That's 0 seems sus. Because this is going to be, it's t, right? So this is going to be 1. 1 of, oh, wait. Wait, this is going to be t of 0 plus minus t of 1 t. So this is going to be minus 1t. This is going to be, this goes to 0. And then this becomes t of 2 t squared. So yeah, so this becomes, so then yeah, t does go to 0 minus t plus 2t squared. Okay, so then I think we do have our basis. T of b, t relative to b is equal to the matrix. The first column is going to be 1, minus 1, 2. The second column is 0, minus 1, 2. And then the third column is 4, minus 4, 4. All right, so we finally did that problem. This problem took a long time, but it was actually really fun, so I don't really regret it. Okay, so it's going to do a ton of algebra here. Yep, we did that just with full simplify, which was sweet. Yep. Oh yeah, I forgot to write. Is an eigenvec with lambda equal to 1. That's what I wanted to write. Okay, then here, one minus 1. Oh yeah. Yeah, this is 1. How do we do this wrong? 1 placed with 2 is just 1. Okay, yeah. So that was just a little mistake. And then here, 0 minus 1, 2. That's correct. And then I did this one wrong as well. So t squared replaced with 2, you're going to get 4. Oh, yeah, p of 0. Oh, yeah, okay. All right, I did this wrong. Because I was doing it like t squared is going to go to t squared replaced with 0 minus t squared replaced with 1 times t plus t squared replaced with 2 t squared. So this is going to be 0 minus t plus 4t squared. Okay, so this is 0, 0, minus 1, 4. Okay. Cool. That was a tough problem. I think we spent maybe like 30 minutes on that problem. Oh, hey, what's up, Yang? What's up, Kevin? I finally got for some reason my chat wasn't showing up for the longest time, but now my chat is showing up. It's pretty cool. All right, so we're doing linear algebra. So we finally did problem 4. So let's do problem 5. Oh, I love the spiral on this notebook. The spirals on my other notebooks just don't work. Okay, 5. Let B B1 to B3 basis of V. Find T of 2B1 minus 5B3, where T relative to B is equal to the matrix 1, 2, minus 3, 0, minus 4, 3, 2, 0, minus 1. Okay, so in this case, what you need to recognize is that this can be thought of as x relative to b. So we can say x relative to b is equal to the vector 2, 0, minus 5. That's cool. Now, we can just so hold on. So t of let me switch over to this. Okay, we have t of b times x relative to b is going to be equal to t of x relative to b. So just multiplying these two is not going to give us what we want, I think. I don't know if that's correct, but I think it's right. But maybe I'm like confusing something. No, yeah, that's right. C is the B matrix of, where does it say that? C is the B matrix for the transformation. So we have the right diagram, but we don't have P. I think what we can do is, so this vector, this is going to be a vector, and it's going to correspond to, okay, so I think I know what to do. So I think what we can do is, so x is equal to 2b1 minus 5b3. That's not that important, but it is the definition. It is how it's defined. So, but what I want to do is compute this. So this is going to be 204 plus 15 or minus 15 and 5. And this is going to be equal to 17 minus 15, 9. And so this is going to be equal to t of x relative to b. So then t of x is going to be equal to 17b1 minus 15b2 plus 9b3. This is what I think the answer is. Let's double check. We are actually going to use the book. The end of the book has answers for odd numbers. We need to go to chapter 5.4. 5.4. Oh, yeah, baby. We did it right. It's good stuff, man. Okay, so we did problem 5. Problem 5 was actually pretty easy. Let's do problem 7. Okay. We're doing problem 7 now. Okay. Find the B matrix for the map x goes to AX for basis B equal to B1, B2. Okay. Four, 9, 1, 4. And then B1 is equal to 3 minus 1. Okay, so we need to find the B matrix. So that means A, B. So if we let P equal B1, B2 equal to 3, 1, minus 1, 3, then what this matrix represents is it will take, so P times X of B in B will equal X. So if we have some vector X, like, hopefully this thing spans, actually, let me just quickly check the rank of this on my computer. Rank of 4, 9, 1, 4. Okay, that's rank 2, and then rank of 3, 1, minus 1, 3, 2. Okay, good. So we're good there. So everything's all nice. So if we pick some, like, if we took like X equal to, I don't know, 2, 5 or something, then what we want to know is, you know, let's say C1 B1 plus C2 B2 is equal to 2, 5. So this is going to be also written as basically P. Let's call this just B, I guess. Or here, we'll do this. We'll call it P because it is P times C1 C2 is equal to 2, 5. So C1, so we can say XB is equal to C1 C2, and you solve for that. So that's just a refresher on what these matrices actually are, because I feel like change of basis is kind of the hardest concept in linear algebra for me. But you know, because it's just kind of like, I don't know, it's just kind of wonky. All right, so my page still showing. All right, the next step. So in order to find xb from x, we need P inverse. So this gives us the equation P inverse times x is equal to xb. Why does the frame rate seem kind of low? I wish this thing could do 4K 60 FPS. That'd be so badass. I don't know why I need that for doing math, but it would be nice. Okay, but what? So the B matrix is the matrix that sends x relative to b to t of x relative to b. Oh, okay, so x is just going to be equal to hold on, let's do it this way. So if we multiply both sides on the right by p inverse, we're gonna get a p inverse is equal to p inverse x, and then we can do left. So we're gonna get x is equal to p a p inverse. So so then we just do that. So so if a is equal to this and b what are we going to call this? We're going this p is equal to this. Then we can do p times a times inv p is equal to 7801. All right, that's problem 7. Let's check the back of the book. 0. Wait, I got it transposed. How did that happen? I got it like transposed with a row flip. That's weird. What? Oh, wait. Okay, I forgot about this. I'll be right back. Hold on. and then expressing each result in the basis. Oh yeah. Okay, I think I get it. Because A is going to be equal to P X P inverse. Okay, all right. Yeah, you got to be careful, man. You got to be careful. I get it. Okay, so we're good. But the other way to do this is definitely the better way, though. But is you basically is you say AP Um, wait. Is it? Wait, if you have an x, then you need to apply p inverse. So you get p inverse. Then you get x, then you get p. So it should be px p inverse, right? What? Wait. Oh, that's x is equal to no, but a. Hold on. A is equal to px p inverse. Yes. Okay, that makes sense. But I do want to understand this part. So he's saying that's weird. So they're saying it's saying wow, that's crazy. So we take the other way of finding that's what I was looking for. So you do so this is wrong. That's okay. It's so wait. There we go. Okay, cool. That was a good problem. Let's do number 8 just for fun. 8 will be really short because now that we've worked through all the pain. So we have -1, 4, -2, 3, and P is equal to the B1, B2 columns is equal to the 3, -1, 2, 1. Okay, so now we can just do P is equal to 3 -1, 2, 1. And A is equal to -1, 4, -2, 3. Okay, so now we can just do this. And we'll get, so then P backslash AP is equal to X is equal to 1, 2, -2, 1. Okay, so we did 7 and 8. Now we're going to do 9. Okay. In exercise 9 through 12, define T from R2 to R2 by the matrix of multiplication. Find a basis B for R2 with the property that okay, so we need to find, so in 9 we have A is equal to 0, 1, -3, 4. So if we do A is equal to 0, 1, -3, 4, and then we just do eigen of A, then we should say that for eigen of A, I think this is square root of 2, right? Or no, it's square root of 2 over 2. Yeah. Then P is P is this. P is -1 over root 2, -1 over root 2, then some random thing, -0.31 and -0.94. And D is equal to 1, 3 with zeros on the off diagonal. So if we were to check the answer here for 9, we should get wait, what is 9? 9 is find a basis. Oh, you know what? You know what? I think I know what happened. If we did this in Wolfram, it wouldn't normalize the eigenvectors. So if we said A is equal to 0, 1, -3, 4, and then we did eigen system of A, we would get 3, 1, 1, 3, 1, 1. Okay, cool. So this is actually, are they column? I always forget if they're rows or columns. So I think, hold on. Okay, so the vectors are given as columns. Okay. I didn't know that actually. So 1, 3, and 1, 1. Good. Okay, 11's the same, so we could skip that. Mm. Okay, I'm going to end the stream now because it has been 1 hour. But this is a good stream, actually, I think. 3 hours of change of basis stuff.